However, what I'll be talking about now is, of course, problems where the state space is very large. And I'll just make a brief comment on it. It's ideally not a part of the syllabus because machine learning cannot be a prerequisite for this part. I'm speaking more because you have learned machine learning, so it's good to speak more about what do we really do when the state space is very large. So now you take in things like a video game. So what's a state? Anything that you see on the screen, it encodes everything. It's a good enough representation. That's how humans play. They look at the state, what is there on the screen, they take the action. Things like score, timer, everything is encoded out in that picture. And similarly, for the other example, a robot is going, it's taking images from HD cameras, it's taking depth images from HD depth cameras, it's taking a lot of sensor and it just needs to take in an action. So the state is everything that the robot sees using all the sensors possible. So we're talking about humongous state spaces. We're absolutely talking about state spaces where the size is terribly large. And because the size is terribly large, of course, I need to do something, and that something is a very own old known technique. So the moment in problems, your state space becomes absolutely very large, you do a feature extraction, and you get a feature vector. So state which maps to a state space, a set of all possible state, is huge, but feature which maps to a feature space is absolutely small. So instead of taking QSA, all that you do is you take Q of feature space of SA, where F is your feature extractor. Now I'll make use of one thing which by now you have an idea from the machine learning course, and because you have an idea from the machine learning course, I could make a brief comment upon it, is that how do I really deal with this problem? And machine learning also does feature extraction. Neural network first extract features and then using a simple transformation map it to the output space. So I make in a neural network. So this could be your ANN or deep neural network. It takes the state as input and it gives as output the Q values. And because it's based on the state and the action A, I say, okay, let action A also be an input. So, interesting little thing. So, video games, I'll just take the state and my action, which is which key was pressed, and give it to a deep neural network, CNNs, whatever, and get the Q values. Robotics, I'll just take all the sensor readings, give it to ANN, give it to DNN, and I'll get the Q values. The other way now it could be interesting to observe is that eventually video games, robots moving, how do they really do it? Supervised learning, I'll have to write down a program, I'll have to get a lot of annotated data of humans playing. If it's a good video game, a lot of humans will play. If it's a bad video game, nobody will play, like teleoperating the robot. What's more is, how do you get good players for a game? If they were good, they wouldn't be volunteering for you, they would be millionaires. Most of the games, the best players don't even exist. All players are bad, and tournaments are selecting among the bad players. The best player is a computer who will defeat all current players by some time. So the data that you're getting online by people playing, it's bad because your players are bad. So these are problems which cannot be learned by supervised learning. They absolutely cannot be learned by supervised learning. They could be learned to some extent if you get a lot of volunteers and those are somewhat good. So this is what is the modern new. So whatever the robot senses, I'll just pass it over here with all the possible actions, and whichever gets the best Q value, I'll just select that up. So my action selection is same as previous, except for there it was a Q was a Q table. Now Q is just a neural network like this. It doesn't make a difference in any of the equations. The learning is also pretty much simple. So what was our learning equation? Whenever I'm drawing an arrow, it means the old value rewritten by the new one. Observed. So that was a learning value. Now I would have loved to compare it step by step to a learning value that you saw in supervised learning at the other course, except for what if I take the loss function as then you see the derivative that you do in a normal neural network is exactly the same equation. And this is learning one data. So it's exactly the same thing. So all that I need to do is I need to learn a neural network on this as the loss function. It's even more interesting. So all neural network, if you supply a target, you know that standard machine learning libraries can learn it. The only thing that I do is for this input, I supply this as the target. Everything is known. SAS dash is known. RSAS dash was observed, and this Q I will be able to use exactly the same thing and get that. The only thing that you need to do is that if you are too formal and you end up taking a derivative of it, you know that this is the same Q function and this is the same Q function. So you take this as a constant and this as a variable. So a derivative of this will not be taken. Otherwise, you will not end up in an expression. So we don't need a neural network library. We don't need a reinforcement learning library. Any neural network library can also perform reinforcement learning. For this data, just supply this thing as the target and learn that up. So get a live data. In that live data, set this thing as a target and have one iteration of a backpropagation algorithm. That's how it goes. So the same figure once more. So I do action selection. I implement the action. I observe S dash and reward. And I set target as this one, and I learn one piece of data. Then I'll do it once more, I'll get another piece of data, and that's what the machine learning people would have called as sequential learning or iterative learning or learning with a batch size of 1. If you want, you can pool it and learn it for greater batch sizes as well, and that's the best thing that you could happen that you could do. One difference that you observe in contrast to classic supervised machine learning is that in supervised machine learning you have all the data and then you learn it up. Here you're generating data, learning data, generating data, learning data, generating data, learning data. So every time you learn, you generate more data, you learn that, you generate more data. So it's not like a human has given you a data collection. It's not that the human has annotated some data. You generate data from the simulator, you learn the data. So when you do supervised learning, you're hunting for data. You're making a lot of calls. You're calling up the application specialists. You're begging for data. Here, you just need an environment or a simulator that keeps on generating data, and you learn that. The problem. So, in supervised learning, unsupervised learning, your target was fixed. Here, target keeps changing. And believe me, imagine a kind of a learning framework. Imagine any kind of learning where I tell you that 1 plus 1 is equal to 2. You learn 1 plus 1 is equal to 2. Come to me very happy, I learned that. Now I say, excuse me, 1 plus 1 is 1, 0. I didn't tell you the decimal system. You learn 1 plus 1 is 1, 0. I again set the target again. I change the target. So 1 plus 1 is B. So what will happen when the target keeps on changing? Eventually, using the same notion, I could tell you that it converges. So the goal is fixed. So things which are neighboring to the goal will have a terminal utility which will converge, and their neighbors will eventually get converged. So yes, convergence eventually happens. However, for everything, the target keeps on changing. And because the target keeps on changing, unlike supervised learning where you see a nice trend, reinforcement learning is more chaotic. It seems to have learned, seems to have learned, seems to have learned. Something changes that affects the broader area, so it needs to be relearned. The target changes. I'm not going into much details of it. Reinforcement learning is a full course in itself at all the other universities. Unfortunately, not with this university. So I just tell you the basic points. So something what you do is that because the target keeps on changing, so you say that let's keep the target as constant. And how do you keep the target as a constant? By writing something on top of it. So instead of one ANN, you take in two ANN. So that's your first ANN and that's your second ANN. This is Q actor, SA, and this is Q critic, SA. So what happens is that the critic only supplies the targets. The critic only supplies the targets. So when the actor is learning, for target it's using this values. And because it's using this values, so the target becomes constant. And because the targets now become constant, so you don't have the problem that the target keeps on changing. 1 plus 1 is 2. It will remain as 2. Good. But then there's another problem that actor learns to imitate critic. How does the critic learn? There are two neural networks, both need to learn. So I basically fix a random critic and then I learn from critic. So this remains random and this one improves. Then what do I do is, after some time, I copy the actor back to the critic. So they both become the same and then I learn keeping this as fixed. So it's like a step-by-step thing. So you're learning based on a critic which is constant, you keep on improving that up. Then when you're a wise man and your critic is a dumb person, you give your knowledge to the critic, copy the weights, and then you again start learning. So it provides some stability. When the actor is learning, the critic makes sure that the target is fixed and there is stability for the time being. Then you improve the critic and then you continue to learn. And this goes on pretty much for cycles. So I mean, another thing that you could do is that this thing would be absolutely terrible, that you can see that you generating one data and you learning one data, then you generating a second data, you learning the second data, you generating a third data, you learning a third data. What if I need the entire batch like a supervised learning? Many people come from that, so they're like, okay, give me a batch to learn, don't give me one data. Who learns that anyways? I give you question 1, you learn question 1, then I give you question 2. No, I give you the entire syllabus. Examinations coming up. So you make a table, and this table is like this. So this is the supervised equivalent of the reinforcement learning. From state S, I applied the action A, I went into state S dash, and the reward observed was RSA S dash. So you make an entire table like this. You have the inputs. The problem is there are no targets. This table only has inputs. It doesn't have targets. So you of course sample out random data from this table for your mini batch learning, for your batch learning. And once you select this data, then you get in the actual table on which you will be performing supervised learning. Now I'm performing supervised learning on selected data. So now I need the input and I need the targets. What is the target? The target is simply, available from this table plus constant So use the critic network. From the critic network, calculate this value. So the critic fills up all the targets, and then you learn the actor in a supervised learning, and then you continue learning from based on that. So this one is what is called as a memory replay. So it gives in some batch processing kind of a technique in order to perform a reinforcement learning. Okay, so finally summarizing, what did we do in a reinforcement learning? All that we said was that the problem is into two parts. How do I select the action and how do I learn from the action? How do I select the action? A mixture of exploration, take a random action, easiest code to write, and exploitation. Look at all the Q values and take the best codes to write and take the best action. It does not matter how is your Q value stored, as a mathematical function, as a table, or as a neural network. The other problem, how do I learn? So if it's as a table, you could just use the temporal difference learning equation. It learns faster than all the other techniques without requiring a model, because the Bellman equation is embedded inside it. And because of that, it could just simply learn it up. How do I get rid of probabilities? Because God selects states in such a way that the probabilities are naturally represented. If your state space is large, then you could just model the Q-learning as a neural network and use a standard neural network library, setting the targets as defined by this, and do a normal learning in any one of the formats. One model that we did not discuss is called as learning policy. So this is learning the Q values. I can also learn policies. So the input is the state S, the output is the policy. So where pi A1S is what is the probability that I select the action A1 given the state S. Earlier I defined policy in this way: best action possible That's called as a deterministic policy. This one is called as a stochastic policy, where instead of selecting the best action possible, I say by which probability should I select the action. So it's same as classification. So some people would define it as a posterior stochastic. Some people would define it, the output is a label, deterministic. So, and these probabilities are the ones that I need to compute. The reward at every time is that I took this action with this probability, I took action A1 with this probability times the reward that I observe. I took an action A2 with this probability times the reward that I observe, and so on and so forth. And this could be similarly learned like the neural network. So similarly set the targets. The only difference is now your outputs become the probability of the selection of the action. And the funny thing that goes around over here, just skipping it up entirely, not into the syllabus. So you make the agent move and you observe what is the total summative reward that it gets, what's the indicative probability. Then you look at which probabilities got fired. If this value is good, you try to maximize it. If the summative reward is bad, you try to minimize these probabilities, and that's how you set which of the probabilities are likely and which are not. So your loss function just becomes the probability times the total reward, and you take a backpropagation of it where the reward is a constant. So you just backpropagate these outputs around over here. So this one is called as the direct policy estimation. And a backpropagation algorithm applied on direct policy estimation is also called as a policy gradient, because the loss function is policy times the total summative reward. A gradient of that is a gradient of the policy, and that's exactly how it happens in neural network. You take a gradient and you backpropagate that up. Ending up on a reinforcement learning with a quick note that one thing which we still have assumed and it will remain assumed is what is the reward function. And that's one of the most difficult things in reinforcement learning. How do you define what's the reward function? So supervised learning, if you get parameter something wrong, machine will still learn. The human annotators decide what's the target, so that's assumed. Unsupervised, they are natural patterns. If they are there, the machine will exploit it. Reinforcement learning, everything is dependent upon reward function. If your reward function is bad, you get bad output, and there's no declining it. Like what we are doing over here, I have a bad game, I set a bad question paper, the rewards that you get are naturally bad. And because the rewards that you're getting are naturally bad, the bad student is becoming topper, the good student is getting down. What happened during coronavirus? So, if your reward functions are bad, your machine learned will be bad. There is no other quality control than controlling the reward function. These days we talk about something called as inverse reinforcement learning. So, things like this, you got a supervised human tagged input. You learn some preliminary model supervised, and then you try to extract out what is the human trying to maximize, minimize, and that becomes your reward function that you try to work upon, which is the one that gives you the actual reward function that will hopefully be good for your own specific problem. So with this we end the reinforcement learning on exactly this note.